All right, hi everybody. I'm going to be giving a talk about entitled Virtuonoid Breaking Out of KVM, the Linux kernel virtual machine. So what exactly is this KVM thing and why do I care about it? KVM is the sort of the new hotness for virtualization on Linux. It's a virtualization system that was developed sort of from scratch to be the official in-tree, supported by upstream, working friendly with the Linux community, virtualization solution that sort of started later than Zen and everyone else, but has ramping up speed and has sort of become the officially blessed platform for a lot of distributions to do virtualization. And so it's an exciting new platform that I think is going to be seeing a lot of attention in the security space soon. And so I decided to take a look at it and come up with some conclusions and share my results here. So who am I and why am I talking at you? My day job actually has absolutely nothing to do with this. I'm a kernel engineer at a company called Ksplice, but it does mean I spend a lot of time staring at low-level software systems, and so in my spare time I tend to do a lot of low-level security stuff, including this work on KVM. All right, so structure of this talk. We're going to start by taking a high-level look at KVM, at this Linux virtual machine. We'll look at what the different pieces are and how they fit together, and then we'll go back and focus in on each of them from an attack surface perspective. From an attacker trying to break out of a KVM virtual machine, what's interesting about each of the components, how are they exposed to the attacker, what kind of things should we be thinking about and looking for. And then we'll run into a deep technical dive into the guts of actually writing a breakout exploit against KVM, learning in the process a bunch about some useful features of the KVM architecture that come in handy and that we can exploit in creative ways. We'll start by just looking at the bug that my exploit centers around, and then we'll just talk about the actual exploit that I wrote. Then I'll discuss some conclusions that I think are sort of implied by my work or suggested, and some future directions that I hope to proceed in or that I would love to see other people do work in. And then we'll demo the exploit, because no talk on exploitation is complete without an on-stage demo to potentially screw up hilariously. It's been reliable so far. All right, so KVM, how does it work? There's three main components to the KVM virtual machine. There's KVM.ko, the core kernel module. Then there's a pair of kernel modules for supporting Intel and AMD hardware support. And then there's the user space driver program, QEMU KVM. Looking a little bit at the function of each of those and where they sit, KVM.ko is the core of the kernel modules, of the kernel side support for KVM. It's sort of responsible for emulating and tracking the virtual CPU and memory management unit, the core of the virtual machine, using the x86, AMD's, and Intel's hardware virtualization extensions. It emulates a small number of devices and input-output operations in kernel directly for efficiency, but for the most part it doesn't deal with emulating hardware. And then it also provides a large interface for a user space driver program, like QEMU KVM, which we'll talk about in a second, to communicate with it, to allocate new virtual machines, allocate new virtual CPUs on those machines, set up the emulated physical memory and all of that. And one of my favorite bits of trivia about KVM.ko is, despite the fact that we're using hardware virtualization extensions here, which means that for the most part, the virtual machine is just executed directly by the processor in a virtual machine non-root context, as Intel calls it. KVM still contains an entire x86 emulator in the kernel module that's used for handling certain rare traps. And just sort of from a code complexity and attack surface perspective, it's an interesting thing to know. KVM Intel and KVM AMD are the other half, really less than half of the kernel component here. They just provide the glue code for communicating with the hardware virtualization extensions. It's, more or less you take those 4 chapters or whatever from the Intel manuals and implement the software half of that, and you get these. And they're relatively small. They're 1 C file, 4,000 lines or so each, which compared to any of the other components is tiny. And then finally, we come to the user space component, QEMU KVM. which is the direct user interface and user driver for KVM VMs. It's based on the classic QEMU emulator, which I'm sure that almost all of you have heard of and probably even used because it's amazingly useful and handy. And in addition to providing the interface and driver loop, QEMU KVM implements basically all of the virtual devices that your VM talks to, because a virtual machine, much like a real machine, is not just a CPU talking to a block of memory. In order for it to be useful, there needs to be peripheral devices, PCI buses that hang off all kinds of devices, your Ethernet card, your display, a serial console, whatever, a timer device of some sort. All of that lives in QEMU KVM, and it's responsible for emulating those devices. And devices are complicated, it turns out, and as a result contains a huge quantity of code. It's an order of magnitude more code than KVM.ko, even if you only consider the devices that are actually in use by a typical VM. If you consider, all of the possible devices, it's even bigger. There's currently a project underway by the upstream Linux community to potentially replace this user space component with a separate, developed more or less from scratch KVM binary that would be maintained in the Linux kernel tree. But that work is relatively new. It's not more than a year or two old, and it's going to be some years before it's stable enough that people are seriously using it, and then some more years before distributions are actually shipping it and lots of people are using it into production. So if we're thinking about KVM, we're thinking about attacking or defending KVM for the near future. QEMU KVM is what we need to be talking about. All right, so those are the three main components. Now we can go back and take a look at each one with an eye for attack surface. KVM.ko for an attacker is a very tempting target because it runs in kernel mode on the host in ring 0. If I successfully find and exploit a bug here, I have ultimate privileges on the host with no further exploitation or privilege escalation needed. However, despite being a tempting target, it's also a bit of a tough target because there's not very much code there compared to this user space component. And what code there is much of that is dedicated to interfacing with the user space component and so is not directly available for attack by a guest. That x86 emulator that I mentioned is definitely an interesting target because there's a lot of code there that is rarely exercised because the emulator is only used in some edge cases. And that's sort of whenever I'm auditing a system, lots of subtle code that's rarely used is sort of the first place that I look for bugs. There have been a number of interesting bugs there that allowed privilege escalation within a guest because of bugs in the x86 emulator. So there is a bit of a track record of bugs. Those aren't as interesting as breakout bugs, but again, it's a hint that this is an interesting place to look. It's unfortunately not the focus of this talk, but it's something that I want to highlight because I think future research should take a close look here. And then in addition to PrivEsc within the guest, just if we're talking about KVM.ko, we should keep in mind that there's also the possibility of privilege escalation in the host because unprivileged users can communicate with this privileged kernel module. Just, another thing to note if we're looking at the whole scope of KVM exploitation. KVM Intel and KVM AMD.ko, the kernel modules that interface with the hardware, are not super interesting targets because there isn't a ton of code there. It's mostly sort of straight line code that just translates between the kernel's data structures that represent the VM and how the hardware wants to model those and just bridges back and forth. But there's a lot of subtlety and complexity in interacting with these hardware components, and so there's potentially scope for some interesting bugs where the KVM is using the hardware support slightly incorrectly or in an interesting or in an unusual way that allows for interesting attacks. But it's not the first place I'd look. And then finally we come again to QEMU KVM, which as you can probably guess by now is the easiest place to look for targets here. Hundreds of thousands of lines of code emulating device code, so the devices are talking directly to the guest via emulated memory mapped I/O or I/O ports. So they're parsing control structures that the guest is exporting and communicating these strange arcane hardware protocols. Lots of interesting code, and much of this code comes straight from QEMU, which is mostly written by one guy, Fabrice Bellard, who is an absolute genius, brilliant programmer, but just one guy spewing out code over years with no one auditing it, bugs are going to happen. The one unfortunate thing about this as attackers is that it is often sandboxed using SE Linux or AppArmor or some other technology. And so if we do successfully break out from KVM into QEMU KVM and get code execution in that process, we'll probably need another privilege escalation attack to get full privileges on the host. Fortunately, we're all running Linux, which, as any Slashdot reader knows, has no bugs whatsoever, so we should be safe. All right, so that's the structure of KVM, and taking a bit of a look at the attack surface. And now we're going to dive in on our bug, which is in fact, and the bug that I used, which is in fact a bug in QEMU KVM, in that user space driver program. I've got here the text from the Red Hat Security Advisory. The bug is CVE 2011-1751. All the major distributions have patched it by now, so you can go look it up. Red Hat describes it as, it was found that the PIIX4 power management emulation layer did not properly check for hot plug eligibility. So what does that mean? First off, what is PIIX4? PIIX4 was an actual physical chip that was the South Bridge in most circa 2000 Intel chipsets. And since it's a South Bridge, what that means is that it talks to most of the physical devices in computers of that era hung off of the South Bridge architecturally. And so the PCI bus, the ACP support, the real-time clock, all of that stuff, the host, the CPU communicates with through the South Bridge. And this is the default South Bridge chip that QEMU emulates. It supports PCI bus and it supports PCI hot plug. It supports in physical hardware. What this would mean is that you hot plug a device, the chip, and the PCI, instructs the PCI bus to electronically disconnect it so that you can pull it out and be safe. In a virtual machine, what this just means is that we disconnect the virtual mappings for those I/O ports and free the memory backing that device. It's expected that the destructor function for a virtual device performs this successful unplugging of everything, but not every device in QEMU was implemented under the expectation that it might be hot plugged. And so many of these destructor functions are no ops or insufficiently clean up state. And that's supposed to be okay because you're not supposed to be able to hot plug these devices. And so it's okay if they don't successfully clean themselves up. But it turns out that, as the advisory says, insufficient checks for hot plug eligibility. The PIIX4 PCI hot plug path, if you handed it a device, an identifier on the PCI bus to hot plug, it would just blindly go and hot plugging it